Okay, so let's begin the Frames lecture. Frames is covered in Chapter 10 in your hand-doing toolbook. And I want to pause here on the opening slide to kind of give you a sense of why and how frames are used. In this slide, you'll see a robot, right? It's not a Fanuc robot, it's a KUKA robot, but it's the same idea. And we have a fixture. We have what looks like the side panel of an airplane fuselage. This fuselage surface, aircraft panel, becomes the surface on which we're doing our work, on which the robot is doing its work. In this case, it looks like it's spot welding, okay? Or drilling. Maybe it's drilling, as it says here, we have a drilling end effector. But what frames allow us to do is to orient our work surface, in this case the aircraft panel, so that the coordinate system is that work surface. So in other words, what frames do is they allow us to make this surface right here, the aircraft panel, the X, Y, and Z coordinate system for our robots. And what that does is it makes programming the robot much easier, more straightforward, more logical, and that's kind of where the idea of frames comes from. Okay, so in this presentation, we're going to talk a little bit about 3D Cartesian coordinate systems, right? That's going to be kind of a review. Because you should already understand and be aware of 3D Cartesian systems. We're going to talk about the different frame types. I'm going to show you how to create a tool, user, and jog frame. Although I'm really going to focus on the first two, the tool and the user frame. We're not going to do the jog frame in the exercises. We're going to talk about saving frame data, and at the end of this, you will know the difference between the world, tool, user, and jog frames. Okay, so first, let's review two-dimensional Cartesian coordinates. Right, we remember these. We've used these since middle school, probably, maybe even elementary school. We have an X and Y axis. Right, the X is the horizontal axis. Y is the vertical axis. X is positive to the right. Y is positive up. And when we plot points, we speak in terms of X first and then Y. So we can talk about 0, 0 being at the origin. And we can talk about a point out here in two-dimensional space being at, it looks like 600 in the X and 800 in the Y. So we would talk about that at being 600, 800. That's the position for that. We go 600 in the X. Then we go 800 in the Y, and that point, the red dot, is 600, 800. When we transition to a three-dimensional coordinate system, right, we still keep the same X, Y aspect of it, X, Y, but then we add a Z, an elevation. So then it becomes X, Y, Z, or we speak in terms of X, Y, and Z. So in this case, this purple point right here is going to be 600 in the X, it's going to be 800 in the Y, and it's going to be up, measured in the Z axis, it's going to be up 600, okay? So we can also speak not only in terms of location, right? This is a location, the 600, 800, 600, in the X, Y, and Z. That marks the location of that point. But we can also talk about its orientation. Now, for a point, the purple point, like we're talking about here, orientation doesn't matter, right? A sphere can be oriented anyway. We don't know what orientation it is unless we have a mark on it to see how that's oriented. But if you want to talk about orientation, then maybe hold up a pencil. Right? And you hold a pencil up in 3D space. How do we say whether that pencil is oriented straight up and down, whether it's laying down, pointing away from us, or whether it's laying down pointing left to right, or some, position at an angle. All right. That's called the orientation. And we talk about orientation in terms of the rotation about the X, Y, and Z axes. Okay. So when we record a position, and this is in with the robot, when we record a position with the robot, we're recording the location and orientation of the tool center point, the TCP. Okay. And that's why in the last episode, the last exercise, when you were jogging, right? Remember when you were jogging and you were picking up the Jenga blocks and moving them, I said for you to be careful of the orientation of the tool when you're picking it up and placing it. And that's because the orientation of the tool is important when you're recording points. How that tool is oriented, whether it's straight up and down vertical, whether it's laying down sideways, horizontally, or whether it's at an angle, is also going to be recorded. All right. So we have to be aware of the location and the orientation. And the orientation for FANUC is the W, P, and R variables, right? So we have X, Y, Z for location, W, P, R. W is the yaw, P is pitch, and R is the roll. Okay. So frames then allow us to define the 3D space that the robot is going to move in. That's all. Okay. So if we look back at this blue box is the 3D space. Okay. And the crucial thing here is that the 3D space, we may not want it to be oriented like we're used to, kind of the horizontal plane is the ground floor and the vertical Z-axis is upwards. We may want it to be oriented differently depending on our work, what we're trying to do with the robot. And you can see here in these blue cubes how this on the left-hand side may be a more traditional X, Y, and Z three-dimensional space. But over in the middle, we have a 3D space that's rotated a little bit. And then again, on the right-hand side, we have another 3D space that's rotated a little bit. And the reason why we would do this rotation and change in orientation for this 3D space is because we want it to match our work surface, the surface on which the robot is going to be doing its work, whether it's drilling, whether it's picking and placing things, whatever it's doing. Okay. And so that is what we call a frame. Each one of these blue boxes essentially is a frame. Okay. And you can see that here, right? This is another example where we see the robot and, imagine that we're picking different things out of these, from these different surfaces. Okay. And, you might wonder why we would do that. We can talk about it in class, why we would do that and show you why, in your exercises, you'll see, why you would do that and how that's done. Okay. So there are 5 types of frames that we have with our FANUC robot. There's the world frame, which is the robot origin. The world frame is the one frame that we can't move. It's always there and we can't change it. So that's kind of our basis, our ground zero, right? The world frame. Then we have tool frames. We have user frames. RTCP frame. RTCP stands for Remote Tool Center Point. And then we have jog frames. You'll notice that with world frame, we talk about the one frame. There is only one world frame. Okay. But with tool user, our remote tool center point and jog frames, there can be multiple frames. We can define a number of different frames, dozens of frames if we need to. All right. So these bottom 4, the tool user, RTCP, and jog frame are user defined frames. World frame is the frame that, it exists with the robot. Okay. And we can't change it. It's also worth noting, all right. And I want to be very clear. I'm going to say this, I know a bunch of times during this presentation and then when we're working. These names sound very familiar to the jogging methods. Don't confuse the two. All right, they are not the same. So we can jog in the world frame, right? We can jog in we can jog in the world coordinate system, X, Y, and Z, and we can jog in joint. You'll notice joint isn't here. So just be aware, when we talk about frames, we're talking about a coordinate system. When we talk about jogging, we may talk about jogging in the world or the user frame, but we talk about jogging using the world coordinate system or the joint coordinate system. Okay? All right. So as I said, the coordinate systems, these define how the robot will move, right? The coordinate systems define how the robot will move, and we have 5 coordinate systems, right? Joint, world, tool, user, and jog frame. These are types of frames. Pressing the coordinate button, as you've already seen with your jogging exercise, is how we toggle between all those. And if you remember when we push the coordinate system, we toggle through all these. You saw it up here on the teach pendant. We would go through. You saw the words joint, world, tool, user, and jog frame cycle through. Okay. So the world frame is the default frame to describe the location and orientation of the tool center point. So we're always talking about essentially this green dot, right? Now, in this case, we don't have a tool. So the default tool frame is the center of the faceplate. That's the faceplate right there, where the green dot is. Okay. This cannot be changed. As I said, the world frame cannot be changed. And with no tool defined, the default location of the TCP is the center of the faceplate, just like I said, where the green dot is being shown. Okay. Now, when we add a tool, the tool is going to stick out some distance, right? And where the tool, sticks out, think of that as kind of the business end of the tool, right? This is where the gripper is going to grip. This is where the spot welder is going to weld. The drill is going to start drilling. It's going to be some distance away from the faceplate. All right. So we define the tool frame where the business end of the tool is occurring. All right. So the tool frame is the coordinate system at the business end of the tool. All right. It's the default point of, we've already talked about the default, but after the tool is defined, it's referred to as the tool center point. So this point right here, this white dot right there, is the tool's TCP, the new TCP, the tool center point. Robots with multiple tools can have multiple TCPs. Obviously, if the tool is longer, shorter, kind of jogged up or moved up or offset. Then we have different TCPs. When selecting the tool coordinate motion, right, the TCP becomes the point of origin. So as it shows you right here, this is our X, Y, Z point of origin. Now, you'll notice that Z by standard, all right, by standard, Z should always be coming positive out directly from the tool. Z is always pointing out straight from the tool. Right? That's important. And it's used to describe the orientation and location of the physical tool on the robot. All right. So the actual tool center point is going to vary depending on the tools that you have. So in this example, we have a paint tool. This is a paint gun. So the TCP may be out here where the ideal distance is from the sprayer is from the surface, right? We don't want to spray too close. We don't want to spray too far away. So the TCP is that distance right there. On a spot welder or welding gun right here, the TCP is going to be oriented on the end of the tool like this. Now you'll notice that Z is pointing out in this direction, right? That's because it's pointing out directly from the the perpendicular orientation of the tool. Not like this, right? But from the faceplate perpendicular out, okay? This is a spot welder, and in this case, the TCP is going to be halfway between the two electrodes, right? Right halfway in between the two electrodes. So it doesn't have to be a physical point. You know, in the case of the sprayer, there's nothing physically there to touch. In the case of the spot welder, same thing. It's kind of the air gap halfway between the two electrodes. In a gripper like this, the TCP is going to be oriented kind of in the middle there, because that's where when the two fingers of the gripper are coming together, that's where they're going to focus or come together to. Okay. So how do we define the tool frame? Well, there are 5 different methods for defining the tool frame. We're not going to talk, you're not going to do all 5 of these in class. You're only going to do we'll talk about the direct entry method, because that's the easiest. And it actually is the most accurate, right? But you will do a 3-point method. Okay. So the 3-point method defines only the location of the TCP. All right, not the orientation of it. All right, the positive Z direction moves towards the work, away from the tool. Right. The 6-point method is basically the 3-point method, but then we add the orientation of the TCP. Right, the roll, pitch, and yaw orientation of the tool. Direct entry method is where we just type in the information, and this is the most accurate direct entry method, and it's the one that you should use if you have data from your tool manufacturer, right? So if you if you buy a tool from XYZ company, XYZ company will tell you the dimensions of the tool and where the TCP should be, and then you can punch those in directly into the teach pendant so that the tool frame for the robot is as accurate as possible. Then we have the 4-point method, and we have the 2-point plus Z method. All right, so creating a tool frame is done like this. We go to the Setup Frames menu, right? Setup from the menu, and then we choose Frames. And then we can hit either F3 or Other, and it'll take us to the tool frame menu, or the tool frame command. Okay. So we go to Menu, Setup, Frames, and then hit F3 or Other, and then that takes us to the tool frame menu. And here's the tool frame menu, right? And you can see this is the number of tool frames that we have, right? It's showing us 10 right now. There's up here you can see 1 through 10. Right? And you can see the recording right now of X, Y, and Z, and then the comment is kind of the name that you give to that tool frame so that you can remember what it is or what it does. Okay? So we haven't defined, you can see from this right here, we haven't defined any tool frames yet. They're all set at 000. Okay? So we choose we hit the detail button down at the bottom. And this is going to take us into the specific, let me go back one, tool frame number 1, right? This is the one that we're editing right there. Tool frame 1. Right? And then this takes us into the tool frame page or view for that specific tool frame number 1. Right now we're in the 6-point method. So we want to change that by going to Method down here and choosing 3-point. All right. And then we can change the comment right here. We want to give it some name that we can remember that makes sense. And then we start to define the tool, the 3-point method. Now, when you do the 3-point method, basically what you're trying to do is you're trying to lay down, position the tool into 3 orthogonal or nearly orthogonal positions around some reference points. So you can see this the vertical, it looks like the tip of a pencil. The vertical pencil point is our reference point. And these become the position of the tool. So the first thing we do is we point the tool down at the tip and record that position. Then we jog the tool and robot out, and we try to lay the tool down into the second position, pointing at and approaching the reference point, and record that. And then we jog the robot back out, position the robot as it's shown in position 3 with the tool here, and then record that point. Okay. The 3 mutually orthogonal approach points, that's ideal, and it's often impossible to reach due to workspace limitations and singularities, right? So we don't have to get it into these 3 perfect positions. Of course, this is a very incorrect position, and that's because 2 and 3 are not orthogonal, right? They're not. Orthogonal means 90 degrees to each other, and these you can see are in line. Okay, so let's watch a little video of this. So we position the robot here. This is approach point 1 on the tip of the reference point up here, and then we record that point. And then we move the robot to this location for approach point 2 and record that point. And then we move the robot to this location for approach point 3 and then record that point. And then we have our tool frame 1 defined using the 3-point method. Okay. And then we can jog in that method. Okay. So, jog using that tool frame. Okay. So to jog using a specific frame, and some of you saw this when you were jogging in the last exercise, to jog in a frame, you need to hold the shift down and the coordinate, right? And that's going to open up this little yellow box right here, just below the jogging method. It's going to open up the box, and you're going to change, see where it says tool 1? That shows us that we're going to be jogging in tool frame 1 when we change the coordinate method, the jogging method, to tool. So you're going to jog in tool frame 1. You're going to hold shift coord. You're going to cursor up to tool 1, and you're going to make sure that says the tool number, the tool frame number that you just defined. Then you're going to release or you do shift coord again to make this go away, and you're going to change the jogging coordinate system to tool. So we're going to jog in tool, and we're going to specify that we're jogging in tool frame 1. I know it sounds complicated. You just have to do it, right? And we'll show you how to do it. User frames can be set up with any location and any orientation, and they're analogous to the world frame, but they're oriented however you want them to be oriented, right? They're X, Y, and Z coordinate systems, 3-dimensional coordinate systems, oriented in space, relative to how you want to do work with the robot. Okay. We can define any number of user frames, a large number of user frames. The default user frame matches the world coordinate system. So this is the default user frame. It's also known as user frame 0, right? User frame 0 is the world coordinate system, and you can't change it. In user frame 0, or the world frame, the origin is at the base of the robot. X is positive coming out. Y is positive to the right, when you're facing the robot, and Z is positive up, right? According to the right-hand rule, we can imagine that. Okay. When we change the user frame, we're going to shift the coordinate system to some point out in space, right? And this becomes the new origin, user plus X. Now notice here, if the X axis is blue. Notice that we've rotated X so that now X is positive to the right, Z is still positive up, and Y is now positive back towards the robot. So we can orient the user frame however we want to. Okay? And it depends on your work. It depends on the work. Right? So this becomes our new user frame. This, we could call this user frame 1. What do they call it here? Yeah, they do call it user frame 1 right there. U frame 1, user frame 1. Right? And you can see the offset from world is 100 in the X direction, negative 10 in the Y, so we're going back a little bit in the Y relative to the world frame, and then 90 degrees rotation about the Z axis. All right. So as I said, the world frame is UF0, user frame 0, right? We can't change it, right? But we can shift it out. So if this is our work surface, if this orange box is our work surface, it might make sense in order to use in order to make our program a little bit easier, right? This is all for programming. That we shift away from the world frame out to our work surface. So this becomes our origin then. And then we have X going along this axis, this edge of the box, and Y going along this edge, and then Z is up, all right? And that will become our new user frame 1. We can set up a user frame in any location with any orientation. This is used when the part is oriented differently from the world frame, okay? It allows jogging along X, Y, and Z axes of the part, right? And this is where this is how it's helpful, right? It has nothing really to do with the operation of the robot. This is all about jogging and recording positions for the robot when you're programming, all right? That's what this is all about. And user frames can be used in a program, as I just said, okay? So when working with user frames, when no data is defined, the user frame location is the origin of the world frame, right? So when we don't have a user frame, it is the world frame that we're using, UF0. The user frame data is a physical measurement back to the origin of the robot, right? That's what it represents because we always have the world frame. The robot controller, the one that we're using is the R30IB Plus controller. We can have up to 253 user frames, right? When selecting a user frame as the job method, the active user frame orientation will define how the robot will jog. No, that's a typo. That should be jog. When selecting user as the jog method, the active user frame orientation will define how the robot will jog. Sorry about that. Get rid of that B and replace it with a G. All right. So there are 3 methods that we can use to create a user frame. The 3-point method, the 4-point method, and direct entry. All right. In your exercises, you're going to be doing, well, you'll do a 3-point method to start with, but later on, you'll do a 4-point method later on. In the class, okay? In the 3-point method, we define first the origin. The second point we define is going to be along the positive x-axis of the user frame. And the third move is going to be in the positive y-axis of the user frame. User frames are very easy to define, right? It does not take a lot of time compared to like the tool frame, which can be time consuming, especially in difficult orientations. But user frame is very quick. So what you're going to do is you're going to jog first to the origin that you want to use for your user frame, and you're going to record that point. Then you're going to jog along the positive x-axis, whatever you want that to be, and record that point. And then you're going to jog in the positive y direction and record that point. All right? That's it. Okay? The 4-point method is just the 3-point method, but then we add a z elevation. We add a direction in the positive z direction. All right, so that's the big difference between the 3-point and the 4-point method. It's not really any more difficult. You're just adding one more point that you're recording. So let's look at that here. So we record the first point, the origin. We record the second point in the positive x direction, right? Same as the 3-point method. Positive y direction is the third point. And then we move the system origin point up, right? Up here. So this becomes the new origin. That's all. Okay. So we're just like I said, we're just adding another point. In this case, the final point is a z elevation. All right. So how do we do that? We go to Menu, Setup. We choose Frames. Then we choose, if it defaults to tool frame, which it probably will because that was the last thing that you said, then you want to go to Other, right? Down here, Other, and choose User Frame so that you can switch it to the user frame screen. And then you're going to go to Detail to go into User Frame 1. And then you're going to choose the method that you want to define this user frame. And you choose that by clicking on Method. And then you can we can choose between 3-point, 4-point, and direct entry. So you choose 3-point. You can define a comment to give it a name, right? I would suggest not using UF frame 1. I would suggest something descriptive. We'll talk about that in class. And then you move to record the first. Well, actually, this isn't the screen. Let me go back here. So you move to record the first point, record the second point, record the third point, and then if you're using the 4-point method, you record the fourth point. All right. So what's the difference between the world frame and the jog frame? All right. The world frame doesn't change. And user frames change, but user frames are also 3-dimensional coordinate systems. The jog frame is used just to give you a frame for jogging in. That's all. All right. So it's the same as a user frame, but it's used for jogging. All right. We are not going to define a jog frame in class. All right. But the book goes through the method for doing that. All right. It essentially is the same as a user frame. Okay. There's a 3-point method. There's a 3-point method, which is the same as a user frame, and direct entry method for setting up a jog frame. Okay. Now, I'm going to go through this pretty quickly because we don't actually need to do this in class, but, it would be good in an industrial environment. Frames are very important, right? They define how the work is being done, and you don't want them to be corrupted, destroyed, deleted, changed, anything like that. So you would probably want to download and back up the frame data that you have, and you can do that with the controller, and this is the method that they go through to do that. So you can save your frame data. Like I said, we're not going to do this in class, but this is the method that you would do this. This is spelled out in your book as well. Okay. And then how you restore the frame data is shown here, these 9 steps. All right. So that is frames. Most of this is only really going to be is only really going to sink in when you get on the robot and with the teach pen in your hand and go through these steps. So with that being said, I'll see you in class.